afternoon. This is Dr. John Bennett broadcasting from sunny Miami. Today we have the pleasure of having John Rogers, who's going to tell us about his flexible skin sensor to detect blood flow. Good day, John.
Yeah, hi. How are you doing? It's good to be here.
John's out in, I guess you're out in LA.
I'm in Illinois, so cold.
Oh my God, yeah. At my age, John, you get confused.
Yeah.
So anyways, John, could you let's start things off by just telling a little bit about yourself, where you're at and your background, your scientific background, please.
Yeah, sure. So I'm on the faculty here at University of Illinois, the Urbana-Champaign campus. My home department is material science and engineering, but I have joint appointments in a number of other different departments: bioengineering, electrical, mechanical, chemistry, so on. And my interest is in advanced electronic materials and devices, with an emphasis on biomedical technologies, implantables, skin wearables for continuous health and wellness monitoring at home, clinical tools, research, grade devices, surgical implements, things of that nature. So I'm very much a device guy. Most of the work, or almost all of the work that we do in this space, is typically involving very close collaborations with clinicians, because they have the best view on where the unmet needs are, and then we come in with novel ideas around device architectures and materials and capabilities to try to address those needs. Before I was at Illinois, I was on the staff at Bell Labs, and so a lot of the research that we have here in my academic group has that kind of Bell Labsian flavor. We're sort of science in the service of technologies that could address grand challenges in human health in particular.
John, I wasn't familiar with the Bell Labsian, as you phrase it, approach to using technologies. They're involved in healthcare a lot, huh?
Well, not so much. I was thinking more Bell Labs in the historical sense of an industrial research and development outfit that is able to do world-class science. I think 8 or 9 Nobel Prizes came out of the labs since its founding to the present time, but really not ivory tower type research, Nobel level research, but in the context of technologies that have utility in our communication infrastructure. So it's that style that we try to embed in our programs here. But the technical outlets are completely different. It's not communications anymore for us anyway. It's more kind of in this medical device area.
Did you notice at a young age that your affinity for computers?
Yeah, my dad had a PhD in physics, and so I've been kind of immersed in a science type environment my entire life. I did my undergraduate degrees at University of Texas at Austin in chemistry and in physics. I was a PhD student at MIT, graduated there in 1995 with a degree in physical chemistry, 2 master's degrees, physics and chemistry. I was a postdoc at Harvard, and then went to Bell Labs after that.
Well, I can't believe I have a BA in anthropology. I'm on the same screen as you. Urbana, that's the center of supercomputers, right?
Yeah, there's amazing, history of accomplishment in electrical engineering, material science, chemistry, physics, and computer science. So if you've seen the movie 2001, HAL was actually built in Urbana. So, I think it's had a really illustrious, history, and it's kind of embedded itself, in the public knowledge around, the history of computer science. Netscape has its origins here, lots of things, YouTube, so on. So yeah, it's a pretty interesting environment, huge engineering college, about 500 faculty. And it was one of the things that attracted me to the place, when I decided to move back to academia from Bell Labs, is the sheer size coupled with the high quality just creates all sorts of really fantastic, collaborative opportunities for doing interdisciplinary stuff. And I think if you want to take materials all the way to medical devices, there's just a lot of, different disciplines that have to be brought to bear, in order to make that sort of a successful effort. And, Illinois has been a great place for us in that sense.
Okay, we'll get to the skin sensor, the flexible skin sensor. And let me try to set this up here. Okay, you get your PDF. My screen share there. Let me try to open this up. Cannot extract it. Hold on. Okay, let me just give me a minute. Is Netscape? They're from Urbana, correct?
Yeah,
They
yeah,
start in Urbana.
that's right. Yeah, a lot of things.
Marc Andreessen, is he still there?
No, he's in California, but he created Mosaic, which is the precursor to Netscape when he was on the staff here. Stephen Wolfram, another sort of computer scientist slash physicist, is still on the faculty. Creator of Mathematica.
They have I guess a very active computer community, obviously, and a lot of research is going on there, medical research besides what you're doing.
Well, yeah. So, I think the data analytics aspect of, a lot of the ways that these devices operate, it's just incredibly essential, so we actually have active, collaborations with folks in computer science to develop algorithms to understand how to interpret all the data streams off these skin mounted, kind of epidermal electronic devices, as well as some of our, implantable systems. So again, it's a really vibrant atmosphere here, and we can pull in the very best in computer science and electrical engineering, get them engaged in these projects, and really add kind of a lot of value, in that sense.
Okay, let me. I'm still working on this here. Let me see if I can.
I can say a few words, just kind of get started on
Yeah,
the.
sure. You could do that, please. That'd be great.
Yeah. So, again, my core expertise is in electronic materials, and that community is pretty robust. Both at the industrial and academic level. Most folks are thinking about, Moore's law type trends in conventional computer chips. How to make things smaller and smaller and faster and more power efficient and so on. And that's really a trend that's dominating the industry. But where we're interested is to address an aspect of the integrated circuit that really has remained static since the very earliest days of the technology, which is that, all such classes of devices are built on rigid platforms, semiconductor wafers. So if you look at your laptop, your desktop, your smartphone, those geometric and mechanical features of the integrated circuits are reflected at the system level in the devices. So your cell phone is flat and inflexible because the guts of it have those characteristics: the microprocessor, the memory chips, the radios, and so on. And that's fine, if you want to put your device into your pocket, or you want to put it in your backpack. But if you want to take that same technology and leverage it for human healthcare, you might want to put it on your brain, or laminate it into your skin. And none of those kinds of deployments or those kinds of possibilities are supportable, or can be addressed with integrated circuits and semiconductor devices as they exist today. Mm-hmm. So we've spent a lot of time and effort thinking about how you can create, a sensor and a transistor and a circuit technology that, adopts the physical properties of biological systems. So for the skin, for example, we focus on making devices super thin, flexible, also stretchable, soft, compliant, air and vapor permeable, so that you can begin to integrate electronics with the skin, much like the way kids' temporary tattoos are laminated on the skin, to establish a really intimate, long-lived, sort of imperceptible from a sensory standpoint form of integration that would be compatible with long-term continuous monitoring and use. And so, I think we've been able to make a lot of progress in that direction over the last 10 years that we've been working on it. And so the result, we refer to as epidermal electronics, offers all kinds of new capabilities in health monitoring, where you can establish data streams that have quantitative correlations to clinical gold standards that you would see in a hospital for things like ECG measurements, precision skin thermography, or hydration assessment or EEG measurement, EOG, EMG, various biopotentials you can measure, skin stiffness, all kinds of parameters that are completely outside of the realm of what's possible with conventional clunky, wristband mounted wearable devices that exist today. So that's a vision for where we think the technology is going into the future. We have had, robust academic efforts in that space, where we're publishing all of our results in the peer-reviewed literature, many papers, over the last 5 years especially. And then, looking beyond just, academic demos to, commercial translation. So we have, a couple of companies in place, startups. We work with large companies as well to try to get this stuff out of a university research lab into the real world. We've done a number of human clinical trials, both in hospitals and in more kind of real world at home settings, demonstrating, the value of this stuff. And, we're pretty enthusiastic about it. I mean, I think a lot of the technology components are coming together. The manufacturing routes have been established. And, I think we're deep into human clinical trials, both at the academic level as well as the startup commercial level. And, our hope and our belief is that it's really going to change the way you think about electronics as it pertains to human healthcare, and that there'll be vast benefits in many ways in terms of how we diagnose disease, how we treat it, how we handle patients in and out of the hospital, and so on. And we're working on a number of different axes, to kind of pursue these things.
Okay, John, I got a workaround, I believe, for your PDF here. I'm going to screen share that right now. And we'll just go slide by slide, okay?
Yeah. So is it up?
Yeah, let me get it up. Hold on here. Okay, do you want me to start with the first slide or the second slide?
Yeah, the second slide is good. Let's just start with that.
Okay.
Try to step through this pretty quickly.
Yeah, sure.
Get to Q&A because I think
Yeah, sure. You see the second slide, right?
Yeah, so this is just recapping what I just mentioned, that conventional electronics is heading down a path of size miniaturization. Makes a lot of sense. It's a huge industry. That trend is going to continue. But if you go to the next slide, we're thinking about a complementary future where the focus is not so much on size and speed and cost, but more on mechanics and geometry and biocompatibility.
Okay.
Where the vision is to try to leverage all the very powerful sophistication in electronics technology that exists in the consumer world and leverage that into human healthcare in a way that hasn't been possible in the past. So we're talking about electronic sheets that laminate onto the surface of the brain to do electrocorticography or stimulation in the context of epilepsy, Parkinson's, things like that, or devices, as illustrated in the cartoon on the right, that, as I mentioned before, sort of melt into your skin and sit there like a kid's temporary tattoo with all the power and sophistication of electronics, but with that kind of tattoo-like format for comfort and wearability, and as a way to eliminate any irritation at the skin interface.
There are some companies putting sensors in clothes now.
Yeah, I think clothes, that's interesting. It's kind of a form of electro-textiles, I think is what that field is sometimes referred to. The problem is clothing is not intimately coupled into your skin. If you think about, the reasons why wearable sensors more or less are failing, it's because of motion artifacts. Right. And an inability to really intimately interface with the skin. And I don't think a textile mount solves those problems. So we haven't spent a lot of time on that.
Okay. Here's the fourth slide.
Yeah, so this is kind of illustrating the concept, this epidermal electronics vision, tattoo-like devices, and just sort of outlining some of the physical properties that we attempt to achieve in this class of technology. That's the vision. The first paper that we published that really, represented a realization of this vision appeared in 2011, just to give folks a sense of the timeline. So this is relatively recent, but it's been around, at least in our labs, long enough that we now, have a broad range of very sophisticated capabilities in this type of platform.
Now, is this embedded like a typical tattoo with sitting down and with a probe imprinting the tattoo?
Yeah, in fact, I have one of the devices. I don't know if you can see this.
Yeah. Okay. Let me get off the screen share. And you have one on your body?
Yeah, I mean, I kind of wear these things around just for fun because
Oh,
they're
cool.
cool.
Wait, hold on. I got to get this, John. Hold on. Okay. Let's see this tattoo. Okay.
So it's
Wow. Now
yeah,
that's actually embedded, or is that like a stick on?
it's like a temporary tattoo. So it's not a sticker in that sense. It's more like transfer tattoo if you've ever played around with that. So
Okay.
well,
So that's erasable. You can, when you're done with it, you can just erase it.
yeah, you can peel it off. I mean, it's not necessarily designed to allow removal and reapplication, although you can do that. These are thin enough that they tend to be a little bit fragile, but that thin, soft geometry is absolutely critical to making them wearable. So, I mean, I've had this one on a week and done several workouts and showers and stuff like that. It's very robust in terms of the adhesion. It reads into a smartphone, an Android phone. Unfortunately, this darn phone is not charged up, but it has the ability to wirelessly communicate with a phone.
Oh, wow.
This is what the device looks like, but prior to mounting. So one of the tricks here, the practical challenge is that the devices are so thin and soft, it's difficult to just handle them. So what we do is we put them on a temporary plastic backing. And so you kind of peel it off on the backside. There's a very mild but biocompatible FDA approved bandage adhesive. It kind of keeps the device stuck on the skin. You apply it, and then there's a top plastic layer that you can peel off to sort of complete the manufacturing. The mounting process.
So there's no power source problem because it can transmit data.
Well, so this particular device derives power from the phone, wireless.
Okay.
So electrical power is wirelessly transmitted from the phone to the device, powers up the radio and the sensors in the device, and then the device is wirelessly transmitting the data streams back to the phone. That's kind of the way it works. You can embed in these same device platforms batteries, but it increases the thickness, obviously, right? The battery technology is not scaling down in the same way that electronics technology is.
Okay. Let me just quickly go to the fifth slide here.
Yeah. So the fifth slide is just sort of emphasizing the points I've already made, is that conventional electronics are formed on silicon wafers, which are basically like plates of glass in terms of their geometry and their mechanics. It's no good for the skin or the brain or the heart. There's virtually no biological system that has that set of mechanical and geometry properties. So what we've done, is illustrated in the next slide, is to try to reformulate silicon away from that wafer-based sort of platter format into geometries that can afford this kind of low stiffness, soft mechanics. And it's not worth going through all the details. But what we do is make the silicon very thin. That's step one. And just by virtue of the fact that the silicon is thin, it's flexible. And then step two is we configure the silicon in kind of a wavy type geometry, bond it to an underlying soft rubber support. And when you do that, you create kind of an accordion bellows sort of in the silicon. And in that type of geometry, sort of hard, soft composite arrangement, you have a material then that offers an effective kind of stretchable, elastic response, even though the silicon material itself still has its brittle character to it.
Have you done any work with graphene? Isn't graphene supposed to be similar to silicon, but even better?
No, I think graphene is way overhyped. Looked at it a little bit. The problem is it's not a semiconductor, so you can't make circuits out of it. You can do certain things in radio frequency technology. You never make a microprocessor or memory that would make any sense. That's number one. Number two is it's not manufacturable. We like silicon because it's building on an incredible base of scientific and engineering capacity that's developed over the last half century, of the electronics industry, global R&D. You're not going to displace that. I think it's unrealistic. So graphene is, a material. It's cool, but I think it has no relevance to wearables. That's
a good point. It has got a lot of press.
Yeah, it's a typical thing. Hype is getting out of control a little bit. I mean, we want things that have an ability to translate into the real world as soon as possible. And if we can figure out how to deal with silicon and make it do what we think we need it to do to integrate with the skin, for example, that's the route we're going to take, because you leverage this incredible manufacturing structure, design tools. A whole industry is built around silicon, and that's not going to change anytime soon. And we try to get our technology aligned with that rather than competitive against it.
Okay, the epidermal electronics slide is up now, the 7th slide.
Yeah, so this is an image, typical device. What I was just showing you is a device like that, but add graphics on top to make it more aesthetic. But you take the graphics away, that's kind of what it looks like.
Okay.
You skip 2 slides forward,
Okay,
slide 9.
9, okay, let me get to that. The old-fashioned way by manual. There we go. Epidermal electronics.
Yeah, it's just a picture of a device very similar to the one I was just talking about and showing you on my arm. It's got the graphics on top. Illinois Pirate, which we made up, is sort of fitting here somehow with the tattoos and stuff.
That's the Illinois Pirate.
Yeah, we made it up. We try to push this as the new mascot, because we don't have the Illini WEC anymore. It's got it with that. But anyway, if you go to the next slide 10 is one of these devices,
Sure.
full radio capability and so on. This is a little bit different in design, but it offers the same soft mechanics. And I don't have the movie embedded here, but this allows one to collect clinical quality ECG. So we see one-to-one correspondence between data collected with this type of skin patch and what you would see in conventional wired up electrodes and bulk hardware.
Wow, and it's transmitted wirelessly to a device.
Yeah, in this case to a PC. So it's a Bluetooth type of protocol.
That's a pretty small. Is there any metal in that? Is that just a tattoo or a little piece of metal there?
Yeah, so here we tried to align the technology with conventional chip scale components. That's kind of what we've done. That's what you see kind of in the center region there. And then these kind of brownish patches, those are actually very tiny filamentary mesh type wiring that establishes the electrical interface to the skin for the ECG measurement. That all the guts of the thing in the middle are amplifying those signals and then transmitting them out at radio frequencies to the computer.
Is that a 1-lead EKG?
It's 3.
3, okay. Do you know which leads? 1, 2, and 3?
1 and 2 are on the outside, and then 3 is sitting underneath the electronics. They're sort of obscured by the electronics there.
Okay, let's see. Which slide would you like now?
Yeah, so the next one shows you your particular area of emphasis. Slide.
Let me see. This is a 10th slide here. Okay, the bio integrated electronics.
Is that the one you want? Neonatal intensive care.
Oh, okay. Let me go back to that one. It's a slide before.
Yeah, it's slide 11 in my deck.
Okay. I'm sure it's 11. And okay. Water soluble silicon.
This is neonatal. Anyway, we don't need to look at that slide. I mean, the point is, for neonatal intensive care, you got lots of straps and wires and electrodes and bulk hardware, and we're trying to move from that paradigm to something that would look more like these highly non-invasive, thin, soft tattoos, and so we have IRB approval, be moving to actual tests in a NICU unit up at Northwestern's Children's Hospital by the end of the year. Okay.
Which slide would you like now?
Well, so maybe this is a good stopping point. I don't know.
Yeah, okay, that's fine. Yeah, that's fine.
But that kind of outlines the technology. Like I said, we're working on commercial translation. We have things going on in hospitals and whatnot. We can do a lot of different kinds of measurements. Blood flow was, topic of one of our latest papers in this area. So there we're using kind of a thermal technique to measure volumetric blood flow in near surface arteries. So even flow at the microvascular level, we can measure that. We have device embodiments that are designed to measure revascularization in skin grafts. We have ongoing animal experiments with that kind of technology. So I think, from our vantage, it looks like a pretty broad platform, at least the concept of this epidermal electronics. And we have lots of different sensor modalities that fit into that framework and provide all of the advantages that flow from being thin and soft.
Yeah, we have one quick question, John. Someone mentioned, okay, since diabetes is basically rooted in a disease of microvascularity, have you guys seen a big application for this device in diabetes, early diagnosis of diabetes?
Well, that is something we're definitely interested in. The question is, how do you do, blood glucose measurement when you don't necessarily have access to blood all the time in terms of a skin patch? So either you have to, think about microneedles or reverse iontophoresis to get access to interstitial fluid, and you make the measurement there, glucose level. Or we have a project sponsored by L'Oreal that involves sweat collection and chemical analysis of sweat. So we have microfluidic channels that we can sort of etch into these epidermal patches, and we use colorimetric analysis chemistries to determine glucose concentration, along with pH, sodium concentration, lactate, and total sweat volume loss. So I think to the extent that one could establish a correlation between glucose in the sweat and glucose in the blood, we have something that would be relevant. That's not the primary motivation for that project, but we are certainly aware of the applications that might exist in related to diabetes, and that's a future direction for us.
Okay. Any other? I certainly personally can see the application for plastic surgeons after they do a graft. They want to really keep a close monitor of is the graft taking or not.
Yeah, that's what we're doing. Actually, we have an interaction with folks in the Army, and there the emphasis is on burns. So same type of thing, not plastic surgery, but same type of monitoring is important.
Yes. Yeah. Okay. Well, very good. Okay, John, I appreciate your time in talking to us, and we hope to keep in contact with any new developments. Just let us know. We'll put you on the screen again.
Okay, good. Thanks a lot.
Okay, John. See ya. I'll send you the link.
Okay, great. Yeah, bye.
Bye-bye.